Should I start or?
Yes, sir, we may start. Yes, you can start, sir.
Okay, thanks. All right, so we left the discussion at this point where I was introducing the prototypical spin glass, the SK model, which, as we've seen, define a class of random distributions. So it is a distribution over a binary vector, but the distributions themselves are random through their dependence in this disordered interactions J, okay, which is called the disorder or quench randomness. We've seen that it is not anymore enough to consider the magnetization to characterize the macroscopic states of this system. One needs more subtle statistic, which is called the overlap, which is simply the angle between different configurations sampled from this distribution. And thanks to this overlap, we realize that not only there is a ferromagnetic phase where there is a non-zero magnetization, meaning a global alignment of a large fraction of the spins, but the paramagnetic phase, which is m equal to 0, is divided in two. One which is truly paramagnetic in the sense that m is 0, but also q is 0. So two configurations of the measure in this region are random, look like uniform plus and minus ones, and also they have nothing in common. They are orthogonal to each other. While here they look random, but actually they have something in common. They live in a sub-region of the space of configurations where they are close to each other. So this divides the space in regions. Okay. Perfect. So just a word. So this model was introduced by Shenton and Kirkpatrick, who are statistical physicists in the 70s. And so still, let's say, during the time where spin glass was just a useless method before it became extremely useful. But people were driven by curiosity and wanted to study this model in great detail, despite it had nothing to do with any sort of application at that time. And so one of the most brilliant physicists alive took the challenge, because Shenton and Kirkpatrick proposed a solution for this model based on a method that I'm going to present, the replica method, but it was not the correct solution. And then Giorgio Parisi came and proposed a more advanced heuristic, the more advanced type of calculations, which are called the replica symmetry breaking scheme. I won't discuss it, but it's a whole theory. And he got the exact solution. So, and then, I mean, it was believed to be the exact solution for 35 years before mathematicians could finally prove that Parisi's solution was indeed correct. Okay, and the goal of proving the correctness of Parisi's solution gave rise to a whole new field of mathematics, a subfield of probability, which is the mathematical study of spin glasses, which gave rise to equally many new mathematical tools than physicists provided on the physics side. So it's really, I mean, the study of these weird systems really helped gave rise to a plethora of new techniques and concepts. So it's a very rich object, this type of probability measure. Okay, so let's see how the SK model is connected to the Spike-Wigner model, the main model we're interested in. So I recall the definition here. So we have a data Y, which has been constructed as a rank 1 matrix XX transpose plus a Wigner matrix. Lambda is the signatures ratio. So here I'm using different notations. I'm sorry. So in the lecture notes, the notations are the correct ones. Here I'm calling the dimension P. It is N in the lecture notes. So equivalently, the Yij are sampled conditionally independently according to this Gaussian measure, where the mean is what we're trying to recover. Okay. Perfect. So I can write down the posterior distribution. So it is the prior, okay, times the likelihood, and I have one term in the likelihood per observation. So I have a product over Ij of my Gaussian, which is this Gaussian there. Okay. So perfect. And so now I want to show to you that it is indeed a version of the Spike model, because you see, I can just do something trivial. So I can develop this square. So this exponential here gives me okay. And now let me consider binary variables. So in the Spike-Wigner model, I want to take this prior to be Rademacher. So I can only take plus and minus 1 values. So this term becomes trivial, it's just 1. So I can absorb it in the normalization constant by redefining the normalization. This term is also a constant with respect to x. So I can absorb it again in the normalization. We're talking about the probability measure over x. So everything that does not depend on x can be absorbed, can be simplified with the normalization. Okay. So this and that term are not there anymore for binary variables. So the only term that survive looks very much like a SK type of interaction. It's a pairwise interaction. And if I develop this term, I replace Yij by its definition. So let's call the ground truth X star, like in the notes, to make the mapping clear. Okay, so if I develop this term, I get Xi Xj square root of lambda over P Xi star Xj star plus Zij. So you see, it's exactly like the SK. We have a term in the SK. We have also a disordered interaction term, which plays the role of the noise in the Spike model. And here there is the equivalent of the ferromagnetic term. This term was the J0 over square root n in the SK. Except that now this ferromagnetic term, so let me just remind you the energy function in the SK model, it was here. We had a random Gaussian term, these Jij are independent Gaussians, and then we had a constant term there with a rescaling by the square root of the system size. Okay? All this for every pair of sigma I, sigma j. Here we have the same. Yes?
Yeah. So typically we see the Ising model on a lattice, but in this case, you're seeing Jij as
Yeah.
dense metrics.
Yes. So this spin glasses that so the SK model is called a mean field spin glass. So mean field emphasize here that the type of model studied by these techniques are models where every variable interacts with all the other ones. It's a kind of dense graph of interactions. Okay.
Yeah.
But of course, you can also study the Ising model on a lattice where every variable just interacts with on a grid on a grid in 3D, and this is you need completely different techniques. It's very different. Yeah. Okay.
Okay. Yeah. I was also going to add that every time I think of mean field, I always think of like a low rank theory.
What does it mean?
That's like my intuition. Like, so if I wanted to solve, for example, the Schrodinger equation, if I have the wave function and then I try to do a low rank, like MPS, matrix product state, it's a low rank theory would be the Hartree-Fock.
Okay, I don't know really this. I mean, I've not studied much condensed matter, so unfortunately I cannot. I don't see this mapping, but I would be interested if you explain me maybe later the connection. I would like to know. Yes, thanks. I will ask you. So you see, in the SK model, we have this ferromagnetic bias here, which is biasing the spins to go towards the same direction, all up or all down, depending on the sign of this J0. Here, it's slightly more complicated in the sense that what I call now the ferromagnetic bias here depends on which I and J indices you're considering. Okay, so somehow it's a bias in the sense that it's fighting against the noise, which is completely random, but now it's not biasing the variables xi, xj all in the same direction. It's biasing the product xi, xj in the direction of the same product, but for the signal. So what induces ferromagnetism in the Ising model is actually in the SK model, what induces ferromagnetism in the SK model is, in the context of inference, the term that contains the information about the signal. It's a term that biases our variables xi, xj, which are drawn from this Poisson distribution, towards the direction of the signal. Okay, it's like if now we were indexing this J0 also by ij, but it's not a random J0 ij. It's what contains the information. Okay, and so you see this term, which is all this, is telling us that xij, the posterior samples are such that they try to align the pair xij tries to take the same value somehow as yij to align in the direction of yij. And in this yij, there is a term contribution, noise contribution, and a signal contribution. And the weight of one with respect to the other is, of course, the signal to noise ratio. If this lambda is very big, this Zij becomes negligible compared to this signal term. And so the posterior measure will strongly bias posterior samples towards the signal, and so inference will be possible. However, if this lambda is too small, the noise term will win somehow, and so inference will not be of a good quality. Okay? But it is exactly the form of an SK model, so it's very natural that you can study spin. You can use spin glass techniques to study inference problems. So here, of course, the mapping between a spin glass and inference problems is on a case-by-case basis. So SK model is connected to Spike-Wigner model. But actually, if you consider other inference problems, you can also realized that there are somehow versions of a spin glass. And by version, usually in physics, you say a planted version of a spin glass. The spike-Wigner model is a planted SK model. What planted means here is that in the matrix of interactions, which is this Yij in the spike-Wigner model, there is what we call a planted term. This is the planted term. It's the one that contains the information about the signal. Okay, is the term that bias towards the signal. Okay, it's what is not noise, and we call that a planted term. Okay. Okay, is the mapping fine? Okay. So really, when you are doing analysis of high-dimensional inference problems of this sort, and your goal is to compute mutual informations, MMSCs, and all that, in this GUIs you are doing statistical mechanics or vice versa. They are very much connected, these two fields. So let me make this connection. Let's write down a dictionary between all the terms I've been employing until now that connects on one side statistical mechanics and on the other side the statistical inference and information theory. Okay. Okay. So what physicists call spins or degrees of freedoms or particles, which are usually denoted by this sigma, like I've done in the Ising model, is what you call in statistical inference the variables to infer the nodes of a factor graph. If you represent your inference problem in terms of a graph, the bits to reconstruct in error correction and communication, or simply the unknowns. Okay, so what physicists call quench randomness or disorder, which usually represent a matrix of interactions between the spins in the model, is played the roles of the data or the observations in inference. Okay, this is the mapping I've just shown right now. And indeed, so in a spin glass, you first draw the random matrix of interactions, and given this matrix, given a realization of this random matrix, you define a Gibbs distribution, which is the measure of interest that you want to analyze. In inference is the same. There is some oracle, some god that said that produces some data according to some stochastic process that depends on the signal, but the data, once you have it in your hand, you cannot change it. Okay, so it's quenched, it's fixed, and then you write down the post-error distribution conditional on this data. So it's you also have two levels of randomness. Okay. What we call the Hamiltonian or the energy function in physics, which tells us how probable is to observe a certain microscopic configuration that we plug in the Boltzmann distribution, is basically the log of the post-error distribution in inference, because I can simply write my post-error distribution P of x given y, which is P of x P of y given x over P of y, simply as exponential of minus log px minus log p. So you see the log posterior distribution plays the role of Hamiltonian. If I write this thing in and then this normalization there, if I use the notation of physics, I call it z of y is the normalization, is the partition function. So okay, what I've done here is absolutely trivial. I just took a Poisson distribution and wrote it in exponential form. You can always do that, but just to see that what we identify as the energy in physics is simply the log of the posterior distribution. Okay. Okay, repeating myself, the Gibbs-Boltzmann distribution is the posterior distribution in inference. Okay. The Gibbs bracket, so this notation that physicists love to use, which is writing an expectation with a bracket like this, is the average with respect to the Boltzmann distribution at fixed choice for the disorder. And the equivalent is the posterior average, which is indeed also conditional on the disorder, which is the data in this context. Okay. So of course, if someone has a question, you can stop me. Yeah? The partition function, which is the normalization of the Gibbs-Boltzmann distribution, is the evidence in inference. And one of the main problem, of course, in statistical physics is to be able to approximate this partition function, because from there you can get the free entropy that we've seen this morning. So you can have access to all these statistical information, the order parameters, and so on. But again, it's a very high-dimensional integral or sum to compute. If you are working with spins, it's a sum over 2 to the n configurations, or if you considering discrete variable, it's over Rn. So it's an exponentially large volume to integrate over, which you cannot do. And this is the same difficulty in high-dimensional inference as integrating the normalization. Okay. Which require compute this normalization because the base optimal estimator is this. So you need the normalization of this distribution to compute this average. Is a very hard task, and that's why in general you cannot do it. Okay. Maybe you can write down an algorithm that can try to approximate it, and it may work and it might not. Okay. And okay, what we call the free energy, or what I call the free entropy, which is the minus the free energy, which is also the log partition function, which is there. This is the log of the partition function, which depends, of course, on the realization of the disorder. And so when there is disorder, I didn't mention for DSK, we usually take the expectation of the log with respect to this disorder. We compute the average free energy with respect to this randomness, which again will give us the average magnetization, including the average with respect to all possible realization of J. So this is the main object of interest. It's really the goal to compute it, because also it tells you what happens for instances of the problem at fixed J. Because again, this object concentrates. It concentrates in this sense. Even if you do not consider the expectation here, you fix a realization of J, but for a large system, if the system is large enough, this object without the expectation will be very close to the same with the expectation. This is concentration. Okay. So this log partition function is, in the context of inference, the Shannon entropy of the data, or up to an additive constant, which is the entropy of the noise. It is the mutual information. Okay. And you can, I will show you later that it's not just an analogy. If you write down the mutual information in inference, it will be directly connected to the log partition function of the problem. Okay. Because in the context of inference, this is the evidence. And you see that if I average the log of the evidence with respect to the data itself, this is the Shannon entropy of the data. Precisely. That's what I wrote there. You have the same structure. You see, if you map Y to J, you have the log of P of Y, which is this log of Zj, and you have the integration over P of Y, which is this integration there. So these two things are the same. Okay. The control parameters in physics are inverse temperature, pressure, etc. In inference, it would be the signal-to-noise ratio, the relative amount of data, and so on and so forth. Okay. The other parameters in physics are the magnetization, the overlap. Here I took the average overlap. Let me show you. If I average 1 over P, I defined before the overlap as the inner product between two independent configurations from the Gibbs measure. You see that these two variables, they have the same probability distribution, but they're independent. So it means that I can push the expectation there and there, but they have the same expectation, so I get this square. Okay, so this is the average overlap. It's the sum of the squares of the expectations of every spin. Okay. These quantities are the analog of the reconstruction error, the mean square error, any error metric, any error of interest you're considering in inference, the minimum mean square error, and so on. In the context of machine learning, it would be the generalization error. You can formally relate the two. If you set up the analysis of a machine learning problem in the language of statistical physics, you will realize that in order to compute the generalization error, this quantity, the overlap between two samples from the measure you're studying in your context, will appear. So the overlap is really there everywhere. The problem of sampling in physics, so trying to obtain a configuration like this, a vector correctly drawn from the Gibbs measure, which is again in general a hard problem, is the analog of computing the minimum mean square estimator. So sampling is like computing expectations. You want many samples to compute the expectations using an empirical expectation. So sampling is the same as getting the Bayes estimator. Okay, so it's a hard thing. Finding the ground state in physics, it's also an important problem. The ground state means finding the configuration that minimizes the energy. Okay, so it's an optimization problem, a constrained optimization problem, because you are minimizing a function over a constrained space. This is a very hard problem as well. For example, in the SK model, if you put the Hamiltonian of the SK here that depends on the J, it's an extremely hard problem, and many computer scientists work on this, because you can, as usual in computer science, you can often prove that if you can solve efficiently one problem, then you have actually an algorithm that allows you to solve many other problems. And the SK model is one such model. It's a model that if you can prove you have an efficient algorithm to find its ground state or to sample it, you can solve tons of other optimization problems. It's called the NP-complete problem. Okay. So finding this ground state is the same as finding the maximum a posteriori estimator in inference. Indeed, this argmax does not depend on the normalization. You can just maximize the numerator, right? This is indeed the argmax of P of y. Sorry. And you can discard this normalization because it does not depend on x. I'm optimizing over x. So I don't need to compute the normalization constant when optimizing. I'm just trying to optimize this thing. And this thing is the log posterior up to this thing I can remove. So you see, this is also the up to the normalization. This is the log of the Boltzmann distribution, is the Hamiltonian. So these two problems are the same. Okay. What we call phase, yes.
Yeah, just one slight comment too. So the sigmas are discrete. They're 1 and minus
Yeah.
1. Plus
Yeah.
1 and minus 1. But the x in general are continuous.
Yeah, I
from a
mean,
Gaussian.
they're not sampled from I mean, you mean the prior can be anything. That you can also consider an inference problem over a discrete set. It depends.
Okay.
I mean, it's the set over which you're trying. I mean, the prior over the unknown variables can be anything. We have considered at the beginning Rademacher prior as well. So in this case,
Yeah.
it's really like SK. So
So when we want to relate it to the spiked Wigner model, though, so this is a continuum.
Yeah.
Yeah.
Yeah. So if you want the mapping to the Spike-Wigner model and SK is really more clear when the variables are binary in the Spike-Wigner model, because this is how SK was defined. But you can also generalize SK and consider continuous valued spins. There are spin classes defined over continuous variables, and then
Yes.
the mapping extends. Yeah.
Oh, actually, yeah. So in a continuum as a circle, basically like an angle, or just
Yeah.
infinity
So
to negative infinity.
There are spin glass models that are called spherical spin glasses, where your optimization is over variables that live on the sphere, for example.
Yeah, like a Heisenberg.
For example.
Ish. Yeah.
For example, yeah. Exactly. So these phase transitions in physics are also called phase transition now in computer science and information theory, also threshold phenomena, and what we call in physics a thermodynamic identity, which is this very important type of identities where you take the log partition function of your problem and you take a derivative with respect to some control parameter, and you get access to the average value of an order parameter. You have a kind of duality, you see, between control parameter and order parameter. It's a derivative with respect to a control parameter that gives access to the dual order parameter, you see, because this H and M, they are connected because in the Hamiltonian, we have a term like this. So each time I take a derivative of my log partition.
नहीं है मेरे घर में मैं हॉल में तुम्हारे लिए एसी लगा के रखूं
Please mute your Arita.
So each time you take a derivative with respect to H, as the H, like this,
Oh, I'm so sorry. I think I muted all, including Professor John Barbier also. Just give me a moment.
sorry, it's fine. I was saying that
Yes.
what I meant by duality between a control parameter and an order parameter is that when in the energy function you have terms like this, where you have some quantity that appears in front of a scalar like this. This is the control parameter, and this is the order parameter. You see that taking a derivative with respect to this control parameter of the log partition function will construct an expectation of the associated control order parameter. So for example, if I can redefine in my Hamiltonian, let's say that I'm not interested to just study the magnetization. Let's say that for some reason I wanted to look at what is I don't know, a quantity that I could call tau of sigma, which is I don't know, some function. Let's say sum over I. Let's say it's still a sum, or a generic function of my sigmas. Then I could simply redefine my model and add a term like this. Let's call this rho. times tau of sigma. I'm adding this term in the Hamiltonian. And you see that now if I take a derivative, so this is called a source, because now if I take a derivative with respect to this control parameter, rho, I will get the average of the associated order parameter. So I will put the 1 over n there. So by just slightly modifying the model, I can have access to any type of statistics I want. So this is in this sense that it's a generating function. Okay. So of course I don't have to focus on the magnetization. And one of the problem in physics usually is to identify what is the correct order parameter to describe that captures the physics of the problem. Okay. The analog of these thermodynamic identities in inference is, for example, the IMMSE formula. In the same way, if I take the derivative of the mutual information between data and signal, which plays the role of my log partition function, it's related to the entropy, which is really like the free entropy in physics. And I take a derivative with respect to this control parameter, the SNR, I get access to my order parameter, which is the MMSE. Okay. By the way, this MMSE is directly related to the overlap. Let me show it to you. If I expand, so let me not take G here to make things simpler. If I expand this, so this is the norm squared of the signal, and then I have minus 2 x expectation of x inner product with bracket of x, well, bracket of x is this. Plus bracket of x norm squared. Okay? And now by the Nishimura identity, you remember I can replace the ground truth by a new sample from the posterior. So I can rewrite all this x1, this is my first sample, x2, and this is the same, plus the same thing. So it gives this. So here I use the Nishimura identity to simplify. So you see, this is the overlap that appears. So it's exactly like in the SK model. It's the average of the angle of the inner product between two samples from the Gibbs measure, which in this case is the posterior measure. Okay? Okay. Perfect. Are there any questions on this mapping? No? Okay. Perfect. So let me see. We have just 15 minutes left. What I would propose, if it's okay for everyone, is to stop there, because what I want to do next is to start a more technical part, and in 15 minutes there is not much I can say. Maybe I can do 1 hour 15 for the next lecture, or I can also introduce. Okay, let me say a few words about what we're doing next. Okay.
Sir, there is nothing like that. You can just brief what all we have done in 5 minutes. Then we can finish and we can start new topic, as you are saying, into the next session tomorrow. So there is nothing like that. You just have to spend more time.
Okay.
It's fine.
Yeah. So I will take then a few more minutes next time, so that overall the teaching time is the same. But right now it's a good moment to stop. So basically, what we've done now, I think that I convinced most of you that there is a very natural and deep connection between high-dimensional inference information theory and the statistical physics of disordered systems of Ising type of models. This type of analogies is more than an analogy. These are really formal mappings, and therefore you can exploit the full toolbox of spin glasses to say many things about high-dimensional inference. So what we're going to do next, so I will spend, by the way, most of what I said today is in the lecture notes already. So what we're going to do next time is to exploit this analogy, this deep connection. Again, this is not just an analogy, to derive this result here, okay? Because as we said, this is really the main result, because once you have this formula, you can simply take a derivative of the right-hand side of this replica formula with respect to lambda to get access directly to the minimum mean square error, which is really the ultimate goal in this analysis, okay? But now the point is how to tackle this problem. And the way we are going to tackle this is through a very important method called the replica method, which was devised by a statistical physicist in the 70s and further developed to obtain a very powerful framework by Giorgio Parisi in the 80s. And since that, it has been one of the main tools to analyze high-dimensional statistical problems, whether they come from spin glasses, inference, machine learning. It's a very important concept. Method which is now also used by information theory theorists daily. If you look at many papers in, I don't know, the IEEE transactions on information theory, there are tons of things written based on the replica method, because you will see that the replica method is not a rigorous method. It's very heuristic. You have to assume things which you cannot vindicate mathematically, but it works. And in many high-dimensional problems, it's the only thing you can do. There are no other techniques that can give exact results. And then what you can do is, a posteriori, once you obtain a formula, a guess, let's say, it's more than a guess, it's really a computation, but with this heuristic method from physics, once you obtain a prediction for your object of interest, let's say the mutual information, you can then try to ask mathematicians, look, it's a very important problem. I think the answer is the following. Can you prove it? And now the answer is yes. Mathematicians have developed very powerful techniques to prove rigorously this kind of statements. I've myself worked a lot on proving this kind of things. It's a very interesting field. And usually it's not that you prove that the steps of the replica methods that I'm going to show you are correct. This you cannot. But you can prove the final result in a completely different way. So this is an interesting approach to high-dimensional statistics. You first guess the formula, first derive the formula using physics, and then you prove it using completely independent method that have nothing to do with the replica method. So I will not have the time to present the rigorous techniques, but it's in lecture notes that I've written that I can give you access to if some of you are interested. But I will show you how the replica method works in detail tomorrow. So it will be the most technical day. I don't think, I mean, from my point of view, what we've done until now was not technical.
But for us, last 2 days has also been so technically sound, because we don't much of do as I told you. But today was, yes, I was also able to get something.
Most of the things I've been saying were conceptual things. So that I've done 1 or 2 computations in random matrix theory, but it was mostly conceptual. Tomorrow we'll spend a day on trying to really learn this one technique, this replica method. And then I would propose to spend part of the last day, if so, there are two possibilities. Or the last day we do another technical part on what we call message passing algorithms, which is this Bayesian algorithm this Bayesian algorithm which allows to match the performance of the minimum mean square error estimator beyond this algorithmic threshold. Or I discuss this algorithm a bit, but in less detail. I don't show you the whole derivation, which is pretty lengthy. I show you the algorithm, I give you I explain you the meaning, and then we spend more time on wrapping up by explaining other applications of all the techniques I've been discussing. I could spend an hour and a half on showing you many other applications of these techniques in machine learning, in communication, and things like this. And maybe we could end on this so that you have a broader view of why these kind of concepts are useful. So if this
I think, sir, we all would like to go with option 2. We would like to get more ideas of machine learning applications, how information theory and Bayesian inferences fit to the different communication systems, machine learning, and other approaches. So if we may follow derivation part less, in the last day we can keep it bit light.
We'll do that then. So tomorrow will be the only day tomorrow will be a day of calculations, so have a good sleep. But hopefully by the end of the day you will be able to use the replica method, or at least to read again the notes and understand the replica method by yourself. And the day after we will see many pictures and examples. Okay?
Okay, sir. Okay, thank you. So I thank everyone. Is there anything you were saying?
No, that's all for me.
Okay, thank you. I would like to thank Dr. John Barbier. I would also like to thank Dr. Julio. I think for you, time has also got a little bit more lagged. Is it fine with you, Dr. Julio, or the time has it is odd time for you? Is it?
It's okay. Yeah, it's kind of early in the morning, but okay.
Oh.
The stuff is interesting though.
Thank you for adhering with us, and I have seen how sincerely you have been attending all the sessions. And again, I would like to thank all the participants who have been hearing and trying to catch up with the mathematics behind all the Bayesian inferences that we keep on using day to day into our different applications. But yes, now we are trying to learn more of the mathematical frameworks behind it. So with these words, I wouldn't take much time. We have done a lot of mathematics, and tomorrow is another more derivations, new methods we are going to learn. And definitely, sir, is there any changes in the notes? I have already shared notes in the group. So should I share the latest version also?
The link that I've sent is the one on which I'm working anyway. So if people click,
so I will share the PDF and overleaf link already shared with everyone. So with this, I would like to thank you spending so much time and giving so much energy in deriving all the equations throughout with us. We really thank you so much, and our sincere gratitude to all the participants as well as to the Dr. John Barbier, who has kindly accepted our invitation and has been with us from last 3 days. Thank you, sir, and thank you all the participants.
Goodbye. See you tomorrow.
Bye-bye. Thank you.